Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. Recall that what we have been seeing in the previous lecture was this priority queuing system. Basically we have considered the non-preemptive priority systems with two classes, right. Much like a MM1, now with that there are two arrival rates, one for higher priority, one for lower priority, or priority 1 and priority 2. And we assume that the first model that we considered was equal service rate case, which assumed that for both the priority classes the service rate was mu. We call this as two priority single rate model, and we wrote the balance equation, and very difficult to get a complete solution for the steady state system size probability. So what we defined is, we defined this partial generating functions, and then we constructed the full generating function or the joint generating function, and by differentiating that we obtained the mean performance measures, which are number in the system, waiting time in the system, waiting time in the queue, number in the queue for priority class 1, 2, and these are the quantities that one can obtain. And so we just finally said that this boxed thing is what we are keeping it boxed, because we want to make some comparison with using these things. So that's why we kept it in this form. That's the performance measures that what we could achieve in that, and then we made some observations with regard to the behavior of these performance measures. Of course, much more can be had if you analyze more deeply, but these are some specific observations specific to the priority system, right. Now let us consider the model B, which we now relax the single rate for this service of both the priorities to two rates. Essentially everything remain the same. So the service rates of the two classes are not necessarily equal in general, and that is where is going to be useful. So mu1, suppose if it is the service rate for priority customer 1 and mu2 for the lower priority customers, as usual you define rho 1 by lambda 1 by mu1, rho 2 by lambda 2 by mu2, and rho as rho 1 plus rho 2. Now a similar analysis, exactly we can write a similar balance equation now, but rates have to be appropriated whether it is mu1 or mu2, depending upon whether the service completion happening is essentially what we call a priority 1 customer or priority 2 customer. Accordingly, that only the change would be mu would be replaced by either mu1 or mu2 depending upon the scenario. Then you have all similar analysis one can do. You can define the partial generating function, you can analyze everything, and one gets finally the number in the system, number in the queue for the priority class customer 1 as this, okay, lambda 1 times rho 1 by mu1 plus rho 2 by mu2 divided by 1 minus rho 1. If I go back, this is what we had it, lambda 1, right, rho divided by mu minus lambda 1, that remains here. So this is there. So this is essentially because of these two rates. Now if you substitute mu1 equal to mu2, you should get back the other expressions which you can check, right. So this is the mean number in the queue of priority 1 customers who are there in the queue. This is mean number of priority 2 customers in the queue, and LQ is just sum of these two, right. So, which is the overall number in the system, right. Obviously, there are only two types here. So, this average number plus this average number must equal the overall number. So, LQ would be here. Now, as in the previous case, here also this part is extra, it is for interested, you can look it up. So, this is the probabilities of priority 1 customers in equilibrium is what this expression is. But what we have in mind is this for to do some kind of analysis, what we have is this boxed material again, but now this boxed material is with unequal rates or 2 service rate. Okay. Now, let us consider another model, model C. Here we have 2 customer classes, okay, with respective arrival rates lambda 1 and lambda 2, and with respective service rates mu 1 and mu 2. Service times are exponential, and now customers are served on an FCFS basis, okay, meaning there is no priority here now here, right. There is no priority here that we are imposing in this situation, right. So, it is merely that there are 2 class of customers who are being merged into a single queue, but when they are taken up for service, they are served at different rates mu 1 and mu 2, but the picking of customers for service is on the basis of FCFS. So, there is no priority. Okay. So, this is a simple 2 class model. Remember that whenever you say multiple class, it does not always mean priority customers. Okay. Multiple class could still follow an FCFS business as given here. Now, this 2 class model can be viewed in some sense as a single class MH21Q, right, because the arrivals are independent with rate lambda 1 and lambda 2. Suppose if you merge them together, then you could consider that as if it is an arrival from a single stream with rate lambda. Customers are grouped into single arrival stream, and the service distribution is a mixture of 2 exponential distributions, right. Could with you that each customer is being picked one of this distribution depending upon the class, but here once you group them, but in this as such you do not have the distinction between the arrival units, but in this there is. So, there is some difference, but this can be viewed in this manner as a mixture of 2 exponential distribution is what the service time and a single class arrival. Okay. Now, for this model we are now using this because MH21 we have not dealt with in any way, but this could be dealt with after having seen the MG1 model, which we will do later. If we have the knowledge of MG1, then this is very easy to see how we are obtaining this performance measures, this average performance measures. But right now you take this as if it is something as granted, okay. But you can obtain even otherwise with the current material, but that is a little tedious process. But if you have knowledge about the analysis of MG1 model, then this is very easy to obtain these quantities, very easily one can obtain it. So, you can see that later, but if you want to analyze again you can go back and then you can start from the basic and you can get the analysis, but that is very tedious job anyway. Now, what we are getting here is this as the number of priority 1 customers, mean number of priority 2 customers, both of them in the queue, and this is the total number, right. So, you can look at here what is happening here, right, and you can look at what is happening here in this particular case. Okay. Now, one can show that the LQ here in the 2 class FCFS is always greater than the standard MM1 model, obvious because now the service distribution at least, because arrival you can consider as a single stream, no issue in that, but service is basically it is not exponential, it is a mixture of exponential and hence it has higher variability, then obviously your LQ has to be higher, right. So, this is the 2 class model. So, we have considered now A, B, C, 3 models, 1 rate, 2 priorities, 1 rate which is model A, 2 priorities, 2 rates which is model B. Now, this is two class, no priority, two class model. This is two class FCFS. Now let us make some kind of comparisons and some analysis we can do with respect to these models. First, let us consider the last two models B and C, which is priority queues with unequal service rates, which is mu1, mu2, 2 rate, okay, and with the non-priority one, which is simply the two class FCFS model. Now, as one can show, right, you have the expressions here. Why we kept this box material is to show that you have the expression here and you have the expression here. Using these two expressions, right, one can show that the imposition of priorities, what is the impact? The impact is it decreases the mean number of priority 1 customers and increases the mean number of priority 2 customers. Well, this is nothing unusual. This is also quite you would expect, right? Because in the other one case, like you are treating all of them are equal. In the other case, you are giving some priority, though it is non-preemptive model, but at least, if there is anything, any lower priority customers are there, he jumps the queue, right? Some customers at least he will jump. So, he gets service ahead. So, the number of priority 1 customers should obviously decrease and mean number of priority customers will also be increase, right, for the lower priority customers. This is obvious, but then why the quantification? The quantification is always essential, right, to sure for proving that, okay, now you have the expression, you can show it with expression, this is true. The additional benefit is that if you want to measure, how much it is increasing or how much it is decreasing, then you need the quantification. Just that intuitive idea is not sufficient. This happens with any mathematical model for that matter. So, it also happens here also. So, you could think about in that way. So, this is about priority 1 and priority 2. Now, how does this overall system performance compares between these two, right? For which then we can pick, say LQ again. You can do analysis with WQL or anything because they are all equivalent. You know that if you know one, you can get the remaining 3 as well, right? So, we can do with one. So, let us pick LQ between these two models, okay. Now, you see here this LQ of B is given by this and LQ of C is given by this. So, these two then they differ by a factor this, right, obvious, because this is common. When you divide this by this, right, what you will get is that this divided by this is what you will get, and that is what is the factor here, okay. Now, this is the overall number LQ that we have. Now, we have kept this for comparison purpose here. Now, you can see since these two differ by a factor by this quantity, now this factor will be less than 1, and what would that mean? That means this is the priority one, right. So, overall also there will be fewer number of priority customers. Overall also there will be fewer number of system in the priority queue, not priority customers only, but it's in the queue, overall queue also. Because what will happen to the higher priority customer, lower priority customer in the priority model vis-a-vis the non-priority model is intuitive. You can still measure the how much is the question, that is additional thing. But what will happen to overall, it is not intuitive, right. So, basically then you have to look at here then what is the idea that you can get from here, right. So, this is LQ of B, which is priority model, LQ of C, which is the 2 class model with no priority, okay. Both of them have 2 rates basically. Now, if this factor is less than 1, that means then the overall number in the queue in the priority model will be less than the non-priority one. So, what does that translates to? So, this quantity is less than 1, that is equivalent to saying lambda 1 row is greater than lambda row 1, which is equivalent to saying just expansion of this. Now, just equivalent to saying that if I cancel it out, equivalent to saying this. So, when does this happen? Mu2 less than mu1, that is the idea, finding that you are making in this particular case, right, which means when So, there will be fewer customers in the whole system when there is priority, provided this is satisfied, which means that the priority customers have a higher service rate, right? That is what this means, right? So, this particular thing gives rise to an optimal design rule, which is what is called as the shortest processing time rule, and this is the basis for this rule, right. So, what we are seeing here from this comparison, just this comparison of LQ between these two models, that this will be smaller than this quantity if mu2 less than mu1, that is what we are saying. That is, the priority queue results in less overall weighting as compared to the corresponding FCFS, right. When the first priority customers have a faster service rate or equivalently shorter service time. Okay. Conversely, the priority queue results in more overall weighting when the priority customers have longer service rates. Okay. So, if you want, what is your objective then? When you are designing a queuing system, you will have a certain objective in mind. If your objective is the overall reduction of the total number of customers who are waiting, or equivalently the overall mean delay, whatever in equivalent words you can use, then what you should do? You should give priority to the group of class of customers that has a faster service rate. So, how you will achieve? So, that is what is this rule, shortest processing time rule. So, the shortest processing time means that the faster service rate, right. So, basis for this is basically you can establish by this analysis that you have done so far, right. Some things may be intuitive, some things may not be intuitive that much, but still you can do it via analysis. That is typical, and here also that holds. Here things may be intuitive or intuitive, does not matter, but you can show it in this way, right. You see precisely when that can happen in this case, right. So, this is what is, if you compare the 2-rate priority with 2-rate no priority model, right. Now, let us compare the priority 2-rate with priority 1-rate model, right. Now, you want this 1-rate, now what you will pick this 1-rate, okay. You must make some choice of certain mu. So, there is a mu1, there is mu2 in the 1 model, and there is a mu there. So, now you have to compare. So, you have to pick something. What you will pick? One obvious choice is take the average of these two means, right. So, this is one reasonable assumption, that the mean service rate mu you pick as satisfying this average rate, okay. Or in general you can pick mu to lie anywhere between mu1 and mu2, right. You may not make much justification if you go beyond this rate, but at least it must be between these two, that is clear when you make this 1-rate comparison, okay. Now, one can show, right. So, it can be shown, but of course, these are all some of the exercise problems in your book, but otherwise also one can show if this mu, if you pick not this average, but maximum of these two, okay, maximum of these two. So, the maximum rate you pick for mu, then what happens? Then the measures of the 1-rate model are less than the measures of the 2-rate model, right. And if you pick mu to be minimum of these two, then the reverse happens, okay. Now, if you ask the question, what would happen to such quantities 1 by mu, obviously this lies between mu1 and mu2, and whether in this particular case which model will perform better or worse, has to be, and it is dependent on the parameter values lambda 1, lambda 2, mu and mu 2. It depends on all the parameters, that if mu is strictly between these two, then the comparison would depend on the parameter. Of course, on the one extreme, say if it is maximum, then the 1-rate model is better. If it is minimum, then the 2-rate model is better, okay. But what if in between? Obviously, somewhere it has to make a transition from one model to the other model to show that this is better, but that depends on really on the parameter values. So, this you can do some such things, and this is a summary of these kind of comparisons where we have also added an MM1 model with rate lambda as lambda 1 plus lambda 2 and by mu as the average of these two, weighted average of these two rates mu 1 and mu 2, and A, which we call it A dash now. So, A, B, C is as usual. So, in this particular case, like A and A dash will have the same LQ, B and A dash if we compare, we set, and B and A, we set what will happen, C and A dash and C and B what will happen, and so on. So, this is the summary of this kind of comparisons that one can make with respect to these models. These are the priority models that we have, right. So, priority models, priority systems analysis wise is difficult, but one can obtain certain mean performance measures, and from that mean performance measures you can, for managerial aspects, for managerial purposes, you can draw certain conclusions, and that's otherwise what is the use of studying such models, right. So, you can draw certain conclusions, and by making comparison of these measures under different scenarios and so on to draw some insights. See, this performance analysis or analysis is basically it's up to the in some sense the analyst, how much he puts his brain behind, and then how much he goes deeper into understanding the system, and how much he can unearth the insights from the analysis is up to him, right. So, the more deeper or the more closer you look at it, you will get more insights, typical of any model, any mathematical model per se, okay. But depending upon what is your objective, like you will target such kind of analysis. So, in this case, suppose if you have it in mind something like you have a two classes there, but you don't know, you are not arranging. Suppose if I assign priority, then what will happen, whether I am going to reduce my overall number or not, okay. Now, you can see, for example, if you go to a supermarket, right, customers with less than 5 items are allowed in one particular queue, right, and customers with their bag full of cart full of items, like they will be there in the other ones. Here probably they are not allowed because it is specifically for this kind of people. Reason behind, they expected to take less service time, right, shorter service time. So, you see in the design rule that we talked about, in that SPT rule is essentially applied there, right, because but justification now, like today you ask like what is justification for that, you have to do this analysis and show that yes, this is the justification, right. So, that is what pretty much happening there. So, to do that, to justify that, you need to have this in your hand to say, and that is precisely what you have it in your hand right now, right. Fine, one can go on. Now, there could be some extensions that one can think with respect to non-preemptive. Of course, there are many directions. So, we have dealt with only 2 classes, but more classes obviously one can handle theoretically in principle. Principle remain the same. But we have seen even in case of 2 priority, obtaining the steady state probabilities is very difficult. Now, for more than 2 priority, it is almost impossible in a way, right. It is near impossible because of their multidimensional nature, and you should define multidimensional generating function and what not, like things become complex here. But if you are interested only in the average performance measures, you have a direct approach, expected value procedure that can be used to obtain the mean value measures. But this is not in our scheme, so we are not going into that. But a similar thing we are going to do it for an MG1 model later. So, that time same things can be applied similar to these kind of models as well. Okay. The principle will one has to think, and then we have to adapt it to the situation, right. But of course, the textbook has this thing also in that, so one can have an idea. And further extension could be like, for example, continuous priority classes. So this is essentially in computer and communication system, this is important. These are based on the actual service times, right? Here we know that the exactly how much is the service requirement we know. So then that is what we say assumed to be known. This is if you know the actual service time. Now this leads to what is called shortest job first, SJF rule. Okay. One can analyze using similar thing, and then the multi-server model also one can think with respect to that. Again direct expected value procedure is what one might be interested to do in this particular cases, right. Some non-preemptive systems, and whatever we did over that gives the flavor of how one can analyze a priority system which is non-preemptive in nature, and one can think about extensions on that. Okay. Now the other system, right, we said there are two kind of priorities, one is non-preemptive and preemptive. So non-preemptive we have seen. Now let us brief about what could be done for a system with preemptive priorities. Okay. Now in this case what we have, we take the same model that we have considered. It is a two priority model. Okay. Higher priority, lower priority, there are two rates, mu1, mu2, same Markovian assumptions, everything is there, meaning that arrival process is Poisson process, service times are exponential distribution and so on. The difference only now is that there is no preemption now, sorry, there is preemption now. There is preemption now. The no priority, non-preemptive only we have seen earlier, but now with preemption is what now we are looking at here. Okay. So what happens now? Suppose that a higher priority customer is undergoing a service, a higher priority customer comes, he queues. A lower priority customer comes, he also gets into the queue. Suppose a lower priority customer is being served currently in the service, then a lower priority customer comes, okay, he gets into the queue. But a higher priority customer comes, what he will do is that he will interrupt the ongoing service of the lower priority customer and he will get into the service. Okay. He will get into the fact that already a lower priority customer is in service means that there is no higher priority customers are waiting in the queue. That is clear. So whenever an arrival happens, if it is higher priority, then he will interrupt the service of the lower priority and he will get into the service and his service will start. Now, right. So lower priority units that are ejected from the service cannot re-enter the service until the system is free of all higher priority units. Okay. Now what will happen to the ejected units? Okay. They must start over, losing all the partial work already completed. This is preemptive non-resume, or the ejected units resume service from the point of interruption. This is preemptive resume regime, right. So you have preemptive resume and preempt non-resume. There are two cases here, but here because the service times are exponential, there is no distinction between these two. Whenever the service time is exponential, you know that if you want to compute what is the remaining service time of this customer, it is still exponential with the same parameter. So whenever it is interrupted, from that point if you look at it, what is going to be the remaining service time that needs to be completed, it is still exponential. So whether you start all over or you start from there, in the exponential case is one and the same. So there is no difference, but this difference will come into play in case of service time distributions which are not exponential. That much we have to remember. Now the state space of this preemptive priority 2 class system is yes. So there is a equality symbol missing here. So the state space is now given by this m and n, right, mn greater than or equal to 0 with their steady state system size probability being defined by Pmn, where m is the number of units of priority 1 and n is number of units of priority 2 in the system in the steady state, As we said, there are two rates for priority customer 1, priority customer 2, there are two rates, lambda 1 mu 1 and lambda 2 mu 2, arrival and service rates. And lambda we define to be lambda 1 plus lambda 2, and rho, which is, this is rho 1, rho 2 in our earlier language. So, this is lambda 1 by mu 1 plus lambda 2 by mu 2, which we need to assume to be less than 1 for the steady state to exist, right. This is the usual assumption that we have here. Now, as earlier, one can proceed to write the balance equation. In will be, there are, in all there will be 2 to the power 2, which is 4 sets of equations. If there are r priority classes, then 2 to the power r, that many sets of equations correspond to each of this class 0 0, m 0, 0 n and m n. Okay. And these are, intuitively one can write down. So, this is now it's 2 dimension. You see, in the non-preemptive we had actually 3 dimension, but the third dimension is just 2 values, but here it is, even that is not there, it's 2 dimension, slightly easier to handle in that sense, right. So, you can look at here, say for example, if you look at the state mn, when both of them are strictly greater than or equal to 1, right. So, obviously, whenever m is greater than 1 or greater than or equal to 1, the system size is what we are looking at it. The customer who is in service is actually the priority 1 customer, that you have to keep in mind when you are writing it here. So, suppose if the state is mn, some generic state you assume somewhere well into the domain, into the state space, not on the boundaries. If you look at it, then what could have happened? Mn, there would have been 1 less priority customer, and with rate lambda 1, the state would have moved from m minus 1 n to mn. One possibility. What are the possibilities can happen? Rate priority 1 customer arrives, priority 2 customer arrives, priority 1 customer service completion, priority 2 customer service completion. These are the 4 possibilities, right. We have to look at those possibilities only. M minus 1 n, an arrival of priority 1 customer with rate lambda 1 takes the system from m minus 1 to mn, one possibility. M n minus 1, an arrival of priority 2 customer takes the system from m n minus 1 to mn, right. Or there could be an m plus 1 n in the system, right. Now, since m is strictly positive, the priority 1 customer is in service and he will complete service with rate mu 1, taking this to state mn. Now, whenever these m and n are inside not on the boundary of the state space, then obviously the priority 2 customer cannot be in service. This is a preemptive system, right. So, priority 2, at least when there is at least one priority 1 customer is there, at least one, then the service will be handling only for priority 1 customer, right. So, that is the other possibility is not possible. So, these are the 3 possibilities. Similarly, when it is in mn, right, currently the ongoing service is priority 1. So, with rate mu 1 he can move out of the state, or either of these priority customers can arrive. So, lambda 1 plus lambda 2 plus mu 1 is the rate of going out of the state. So, the flow balance would then be equal to lambda plus mu 1 times p mn equal to this, right. Similarly, for 0 n, so here there is 0 priority 1 customer. So, currently ongoing service is for customer 2 or priority 2, right. How this 0 1 could have reached? There was 1 n, and from there with rate mu 1 you would have reached 0 1, or 0 n minus 1 with rate lambda 2 you could have reached 0 n, or 0 n plus 1 and with rate mu 2 the service completion happens for priority 2 customer and then he will reach 0 n. Going out again is the same thing, any of arrival or service completion of the ongoing service. When m 0, which means there is no priority 2 customers in the system. How this could have happened? With rate arrival of lambda 1, one more customer would have come, or with the service of the priority 1 customer he would have reached m 0. Going out any of these arrivals are service completion of the priority 1 customer mu1. So, you get this and the boundary state gone. So, you have this pretty much this system of equations, balance equations. We said 4 set of equations. Set means here we mean this is only one, but this is really sets. Now, again like the non-preemptive case, here also you can define the 2-dimensional what you have generating functions, okay. You can define, you can simplify, and finally you can get the moments of the number of units in the system. Similar way one can proceed, and this gives us, suppose if I pick the number here L, which is the number in the system, this for priority 1 this will be rho 1 by 1 minus rho 1, and for priority 2 it is this expression. Now, how we are obtaining expression? You have to do this to obtain expression. But what this tells is, look at the expressions for L1. Isn't it look like what you would see in a typical MM1 queue? And if you look at with preemption, that priority 1 customer will behave as if it is a MM1 queue for him. And whenever the system is free, he is free to serve the lower priority customer. Thus, and whenever the system is busy, right, he has to serve the priority 1 customer. Here busy means here that in the MM1 context which we are looking at it. Okay. So, where this Li is the average number of class I customers, and class 1 customers are not at all affected by the presence of class 2 customers. This is true with preemptive case, but whereas in non-preemptive case, the class 1 customer would also be affected by the presence of class 2 customer, whereas in a preemptive priority queue, the class 1 customer or the higher priority customer is not affected by the presence of lower priority customers, right. So, this is basically always they are effectively for class 1 customers, it is effectively like their MM1 queue. So, you have a simple MM1 queue, now you are putting it one more class of customers whenever this server is free, like you decide to serve for the someone else stream that could be of lower priority. Now, whenever your customer comes, you will stop him in between and then you start doing this. That is the model that you can think of in this particular situations, right. So, this is the preemptive. Again you see that more than 2, again things become complex, but again one can get in some sense the expected value measures in a reasonable analysis level. Okay. So, this is all about priority queuing systems that of course this can be studied in a general framework, but we have studied in the Markovian framework, so that you know more about the how a general Markovian systems can be handled in that. So, that is what we have done. So, we have mentioned, of course, we have not derived all results, of course, you have to do some kind of derivations by yourself, and you can see that this is what one encounters when you have a general Markovian queues. For example, in a priority things become complex, that is what you have to understand, right, that is it. So, this is all about this priority queuing systems that we are going to see in this course as of now. Okay. Thank you. Bye.